school together with the Marzia, and we are also lecturing. It was a pleasure for me to accept her proposition to make this proposal for ICTP-SAIFR here. And for me, it's a pleasure also to be in Brazil and in Sao Paulo. And so I'm happy to see you. As Marcia was saying, I will mainly talk in this lesson about dynamics. Dynamics, and I will focus on dynamics of supercooled water, but not immediately, because we need to talk about all the stuff that we are using for supercooled water in general for liquid. When I talk about dynamics, since in water the interest is mainly for dynamics a lot in the supercooled region, I will think, now introducing the dynamics, about introducing physical quantities and chemical quantities that are related to the study of the slow dynamics. So when you cool water and you have a range in which the dynamic is slowing down and eventually will become a glass, but then for water we have a lot of problem about that, and we will talk about them. So that we have glassy dynamics, but then we have other complicated stuff intervening, but this is something about water. Now let's start with introducing the subject in general. So today I will talk about the slow dynamics of liquids and about a kind of dynamics that water instead follows when it is in the normal state. So first, a presentation, since I'm here new in this country. Who am I? I am a full professor of theoretical condensed matter at the University of Roma 3 in Rome, Italy. I graduated and did my master at La Sapienza, which is one of the 3 universities of Rome, the oldest one. Then I did my PhD in condensed matter physics at the University of L'Aquila, which is still in Italy. It's 100 kilometers north from Rome. And then I went for almost 3 years to work as a research scientist at the Massachusetts Institute of Technology in Boston, in the Boston area, in USA. I was in the group of Professor Xiaoxin Chen. He's an experimentalist working in neutron scattering, but there I was doing the theoretician of the group. Now in Italy I teach courses of general physics and condensed matter physics. At the moment in my university, which is considered a large university in Italy because it's 35,000 students, so large. Sapienza is huge, 200,000, but it's practically only one, maybe Bologna, a few others. Bologna has 70,000. 700,000, but it's considered a large university. I'm president of this unique guarantee committee, which is an organ of the university that takes care of equal opportunity, so issues related to gender, race, religion, whatever you can think about equal opportunity, and also healthy working condition for students and professors and employees in general. And also, since I also covered this role, I'm very much committed in the advertising of and the problem connected with the woman in science. As you know, women in science is still a minority, at least in physics and chemistry, and so the number has to grow. Engineering is the huge problem, and this is worldwide, more or less. So I sometimes do seminars about this matter. It's important to have also role models so that that the female students can see that other female are professor, full professor, rector, like Marcia, that just became rector of a university. Congratulations, Marcia. And so this is important. I have been also in national commission, very important national commission in Italy. For example, I was in the National Commission for Scientific Habilitation. Every 2 years it changes from 21 to 23. We gave habilitation for people who wanted to become associate and full professor. You go to these roles when you have a high profile, scientific profile. And I was, and I am also in these years, a part of the group of experts of high qualification for the evaluation of the quality of research in Italy for physics. It's a huge work, but we are starting to do 2024 now. With this quality of research, then the university take financement if they perform well in research. Of course, I do that for condensed matter physics, and there are other scientists do for the other subjects. I have authored in my scientific career more than 130 papers indexed in the scientific database, like Web of Science Scopus. My profile is public on Google Scholar. I publish on journal, I've published during my career on Journal of the Nature Group and on Science. I've authored a book, which is this one. Sorry that I always miss okay. I've authored a book, which is this one here on liquid matter. It's a book for graduate and PhD students, and also expert in the fields if you want, for example, to give a course on liquid state. It can be useful for the students to have a book. There was a missing tile with felt. I brought it with the Mauro Rovere, which now he's now retired, but has been for a long time a collaborator of mine and is a dear friend. My field of research is theoretical statistical mechanics. I'm a physicist. I'm expert in the behavior of disordered system, fluid matter, especially matter under string condition, and the fluid that in my career I studied the most is water. I've studied water now for more than 30 years, and my studies are performed with computer simulation. Several of former students of mine and postdoc are active in research, and some of them have a permanent position now. So this is my life scientific life in a nutshell, and now we go to the subject of these lessons. First of all, in order to study dynamics, I have to introduce the subject of time-dependent correlation function. This is a very diversified audience, so some of you probably know them, some other don't, but it's always nice to see a recap or another point of view. I need to introduce them for you to understand when I will show you in the next days the results on water, to understand the deep meaning of what I am showing to you. Otherwise, it remains too superficial. Okay, what are these time-dependent correlation functions? They are important descriptors of the motion of atoms and how these atoms are correlated between themselves. We will deal here with equilibrium dynamics most of the time. So I'm introducing this correlation function in equilibrium. When you have a fluid with no external perturbation, you still have fluctuations that can give us important information on how the fluid perform and its properties in thermal equilibrium. Thermal fluctuations are distributed in wavelength and in frequency. So when we study this correlation function, we can determine the structure, the thermodynamics, the dynamics of the liquid for various wave lengths and frequencies. I was not here yesterday, so I don't know what were saying the other lectures yesterday, but this morning you've heard of this correlation function, the static version of this correlation function. The radial distribution function is the equivalent of what I am describing now, only that now I'm introducing also the time variable, which will become a frequency when we go to some experiment that measure the frequency, okay? So we will study the correlation function of time. We will see what is the dynamics of the liquid with time and at various lengths. So this thing of the lambda is also important that you understand. Of course, the phenomena are related in between them, but this, when you decide to study a phenomenon, the first thing important that you have to understand is what is the time window and length window in which this phenomenon is happening. And so what can I use to study it? Experimentally, so you have to access on those facilities who have this time and the space window. If it's in the Fourier transport space, it doesn't matter. It's going to be omega, and it's going to be k, wave vector and frequency. But still, you have to think about the phenomenon, because if you get for example, the machine wrong, you apply for experiment out of the time window of the thing you are interested to, you're going to see nothing, of course. So I'm always saying it's like a magnifier. You decide how much you want to magnify and how big has to be the window or small in order for you to see those microscopic phenomena you're interested in. This speech might seem trivial, but I assure you that it is not, because sometime in my field I hear people that, for example, talk with others and say, oh, I'm not getting your same result. But of course, if the cross-section is completely different and measures on a completely different time windows and frequency windows, it's of course you don't get them. Okay, for example, an example is this. Let us suppose you have a water diffusing in a place which is done of a lot of pores, in a maze of pores, okay? You can decide to probe what is happening inside the pore. And then, for example, you want to see quasi-electric neutron scattering, which is probing just what is happening inside the pore. Or you want to see what's happening when water goes outside the pore. So you study this correlation on a longer time scale, and of course on a longer length scale. Then you will study still the relaxation times, the one that I will show you talk about today. But you will study the relaxation time of water on a long time scale. The quantities that I study inside the pore and the quantity that I study outside with the longer times are completely different. You can compare them. Of course, each one is telling a part of the story. We can paste them all together and then understand what, for example, water is doing on all time scale in our pore. But it is always important that you keep in mind that there are multiple time scales and that this phenomena has to be analyzed very carefully. And then it's important to understand deeply and microscopically what the cross-section or what the experiment that you are planning by computer wants to measure. So coming back from, of course, this subject is huge. So in my series of lecture, I will focus on some particular results of the dynamics of water, because you can have dynamics of several kinds. And for example, as I was telling you now, we will talk about equilibrium correlators that measure equilibrium properties. So for high lambda and low omega fluctuation in the fluid, they can be treated, for example, like a continuum. And they can be studied with the hydrodynamic equation, which is a subject that I will not tackle. At a wavelength comparable with the intermolecular distance, the local structure of the liquid matters. And here, the continuum picture is no longer valid. And here we have to understand what is happening in the liquid microscopically, because we cannot treat it as a continuum, okay? So molecular dynamics deals with the motion of a fluid due to its own interactions, okay? So no external field in equilibrium. But I can also calculate to study microscopic properties, for example. But this correlation function will, you will see that will help us to focus very much on what is happening in the liquid, also microscopically. So we will mainly deal with the k-omega dynamical region, where the space-time variations are comparable to the mean free path and the mean time between the two collisions. So it's exactly what I was telling you before. We are focusing on this length scale for this picture. So no comparison with NMR, for example, no comparison. What measures the time scale we are focusing in is mainly neutron scattering, and some kind of light scattering also could be compared for this correlator and these phenomena I'm going to talk to you about. As I told you, the subject is huge, so I focused on this part. Okay, for this region where I'm focusing, the local structure of the fluid is very important. And if there is some kind of short-range order or short-range correlator, this must be taken into account to study the details of the dynamics of liquid together, of course, with the always existing long-range behavior. Okay, time and space, obviously this correlation function depends on time and space. So what is this correlation function? It's the thermodynamic average of the product of two dynamical variables. In general, a correlation function can be also between different dynamical variables. So let us suppose you are interested in velocity, density. You can also correlate them together, okay? Very often you study the variable correlated with itself. So for example, velocity correlation function, or density correlation function. But you can also mix it in principle. Okay, but in our particular system in which we study the system in thermodynamical equilibrium, what we want to study is the deviation from the equilibrium values, because we are studying the fluctuations, okay? So for example, density. Let us suppose that I have an homogeneous fluid. The density is constant, okay? Let us suppose that I am an isochore. It's constant, but still I can study the fluctuation of density. So I will compare the deviation of density in one point with the deviation from the average density of another point and another time. This is what this correlation function are doing. I'm calculating how is correlated the fact that that I have a certain density in a certain point in space-time where I am, with the fact that she is experiencing another density in another precise point of the space-time. Fluctuation with respect to the average value. We might be correlated, we might be not. So what I will say after, if I am me and she is different from me, this is the self. This is the distinct correlation function. So, and for me to be correlated with her, I have to start a coherent phenomena, because I need to correlate with all the people around me. If I correlate only with myself, then this can be other kind of phenomena, and this is called a self-correlation function. So this is connected to the probability that if I am here at a time 0 and r equal to 0, I will be there where she is at time t at the position r, okay? Instead, the other one, the coherent one, is correlated with the fact that if I'm here at time 0, r equal to 0, she's there at time t, and r equal to r1, for example, okay? So these are the correlation. You can correlate all of these properties, and then you understand what particles are doing. Practically, you can track them, okay? Okay, so it's a product of two dynamical variables. They can be distinct or they can be the same, density, density. Each of them is the instantaneous deviation, as I say, of the properties of the fluid from its equilibrium value in a point of the space-time. Okay, the average is done on the coordinates of the space of all the molecules in the fluid with the equilibrium distribution of an ensemble as wave function. What it means, this sentence? We are doing statistical mechanics here. As you know, the fluid, when I say the equilibrium is a dynamical equilibrium, I move continuously and I have to make an average. For those of you who are physics, you know that, or chemists, that ensemble average has to be done over all the phase space, so all the possible velocity that a particle has. So what does it mean? Since we will talk about the distribution, probability distribution function and ensemble average, just for those of you who are not familiar with this part of statistical mechanics, when I move in a fluid, I can have many velocities, but they don't have all the same probabilities. The velocities that are connected to the temperature where I am are the most likely for me. But this doesn't mean that I could go also very slow for a limited amount of time, for a moment. This is the fluctuation. And then we know that depending on the ensemble, all these properties of the fluid follow distribution function, the ensemble distribution function. So you have to do the average over the phase space, and you have to use the equilibrium distribution of the ensemble that you're studying as a wave function. So you have to weigh that when you are integrating that I'm having a particular velocity, you have to weight it with the probability that at that temperature, pressure, the thermodynamic place where I am, I can have it. The probability might be high or might be low. So in all the integral, you will have also this distribution. Okay, so the time-dependent correlation function is a function of space and time, and then of course you can see it in all the Fourier transform places, and it describes the thermal fluctuation that spontaneously happen in a system in equilibrium. For our particular purpose of this school, we want to focus on the liquid state of water. I will talk about in the other lectures about the liquid state of water. So since I'm focusing on that, water in normal and in supercooled state, the variable observable that we are interested in the most is the number density of the molecules or atoms, I say also molecules because at the end we will arrive to water, in the liquid. Okay, fluctuation of the number density. So we will deal mostly with the autocorrelation function of the density, the density-density correlation function. This density-density correlation function we will be divided, you will see, in two parts. One is the self, so related to the probability that if I'm here now, I will be there later on. And the other is the coherent or distinct, which is the probability that if I'm here now, she will be there at time t1. Okay, so we will at the end arrive, so this subject of correlation function is huge, but at the end we will focus on density autocorrelation function. Okay. Okay, so we can calculate the density autocorrelation function of a liquid in several ways. One way is to measure it with, for example, this one I'm interested in with neutron scattering experiments, or with other probe that have an overlap different from zero with the density. For example, light scattering in the visible region, for example. I don't know whether you know, but the cross-section is related to the polarizability. it's not the density correlation function inside the cross section, but it's the polarizability correlation function. But this doesn't quite matter because the polarizability is related to the density. If I have fluctuation of density, I will have a fluctuation of polarizability. So they are related, but they're not the same. That's why, for example, light scattering experiments are more difficult to interpret than neutron scattering experiments, because then you have to add there also a model for the polarizability. And this gets everything very difficult because polarizability is a very bad beast to model because it has a renormalization in the fluid. It's very hard to model. But anyway, in spite of that, you will see that there are different ranges. There are also slightly different ranges of the famous, enlarging microscope for neutron and light scattering, but still some overlap can be found. So this density correlation function can be measured, or they can be calculated in molecular dynamic simulations. I do the trajectory of the space-time. I decided a potential, make a reasonable guess for a potential. You've heard already my colleague this morning talking about potential for liquids. So you make a reasonable guess, you calculate them, and then you calculate the correlation function. Well, after that, you need a proper theory, because you have this correlation function, you see some changes, something maybe that you do not expect, and then you need a proper theory. So when you have a proper theory, they can give a large amount of information. We will see that we have good theories for the slow dynamics of a supercooled liquid and for the glass transition. What is a time-dependent correlation function? It is like the partition function for thermodynamics, with the only difference that this one can be measured directly, also with the experiment, besides the calculated with molecular dynamics simulation. The correlation function that we will deal with can be measured, as I said, by quasi-elastic and inelastic scattering of neutrons, light scattering, and molecular dynamics simulation. They are, I'm doing this big introduction because they are really ubiquitous in the study of liquids, both for theoretical and for experimental study. So let's see what we have now. We have this time-dependent correlation, space-time dependent correlation function that we can measure with lab experiments or computer simulation. Thermodynamics, structure, transport coefficient go to hydrodynamic and kinetic theories that work for dense fluid, or equation of motion for less dense fluid with an interaction potential that still can give you time-dependent correlation function. So you see that all this part or this part all lead to the time-dependent correlation function that can give you information about the liquids. Now let me spend some time to show you the story of the time window, the space-time window. So borders of this are extending now, so they might be already changed since I last drew this picture, but this is the idea that I want to give you. So you see, here we have neutron scattering and computer simulation. So this is, this is log of omega, and this is k. So neutron scattering and computer simulation, I forgot to write, log k. This is neutron scattering and computer simulation, and as you can see, they work here, in this region. So they do not have overlap, for example, with ultrasonic measurement that are here, with light scattering that are here, and with intermolecular light scattering. When you have this radius, which is circa 1 angstrom minus 1, and you have a tau, which is roughly here, between 10 to the 12 and 10 to the 13 second to minus 1, for omega and k more or less here, you are in the region of computer simulation and molecular dynamics. When k times rc and omega times tau c are much less than 1, you are in hydrodynamic domains. So this is always part of the same story that I was telling at the beginning. You have to know what you are interested in. The fact that your relaxation time calculated here, not compatible with the relaxation time, for example, calculated here, it doesn't matter. You're both right, because you are just measuring a different part of the same huge story, okay? So this is important to have the wide picture for both theoreticians and experimentalists. It's always important to know very well the details of their own work, okay? But still, never forget to also try to understand also a bit of the details of other people's work before saying, no, it's not the same, okay? Because in my scientific career, I have seen discussion going on and on between people that were talking about two completely different probes. So I was like, come on, I'm still doing this. So it's important, if you want to be a very good scientist, remember to have always control of the things. And sometimes, of course, you have to study a bit outside of your single field to understand what are the other things about. Okay, so let's talk now about this time-dependent correlation function. How are they related to molecular dynamics? We will come back to molecular dynamics a bit in the next lessons. But what does molecular dynamics? I told you that besides neutron scattering, we can calculate these correlation functions with molecular dynamics. Molecular dynamics, as some of you might know very well, solves numerically the Newtonian equation of motion for finite time steps. The equilibrium, you must be in equilibrium. So the equilibrium trajectory, for this part of physics we are dealing with, physics and chemistry we're dealing with now. The equilibrium trajectory of the atoms or molecule in space-time are used to calculate the average correlation function in the direct space, which is T and R, or in the reciprocal space. We know that, for those who know statistical mechanics, that we are under the ergodic hypothesis that allows us to calculate the average in time instead of doing the average over the ensembles. So with the molecular dynamics simulation, I will simply run a very long simulations. I will save a lot of snapshots or where the particles are at what space and at what time. And then I will say that those configurations that I saved are absolutely equivalent to an ensemble average. So ensemble average means that I have to give I have to make an average of all the possible configuration of the fluid, weighted with the probability that they get that configuration, okay? With the molecular dynamic simulation, I don't need this distribution because my fluid will go naturally more to the more likely distribution, to the more likely configuration. Do you understand? This concept is very important in statistical mechanics. Have you got it? If you didn't have got it before, because of course some of you have, but it's just for, it's very diverse, the audience, so I'm trying to, do both things. More complicated, and then if you are not so well prepared to that particular issue, it doesn't matter because I will give you the phenomenology, but then we will go through equations through. So we'll do both. This is very important that you understand also how deep is this concept. When you do a molecular dynamic simulation, you already force the system to go in those configurations with the right ensemble probability. So I just do the average of the time of the simulation. If I want to do it theoretically, then I have to take all the possible configuration and weigh them with the probability that they get that configuration for that temperature, that volume, that point in the phase diagram. Okay, Of course, to do molecular dynamics simulation, we have to know the interatomic potential, and then we will come back to how we do simulation molecular dynamics. Okay, why we can also, I told you about experiments measuring the equilibrium thermal fluctuation. And then you could ask me, how come if we are talking about equilibrium? Because if the probe is weak enough, then we have the famous linear response theory that demonstrates that the fluid remains in equilibrium and you still can measure equilibrium thermal fluctuation. This can be shown rigorously with the linear response theory, which I cannot do now because it would be beyond the scope of these lectures, but that you didn't study it, you can take a look at it. This is because the dynamical processes that rule the dissipation of the thermal fluctuation are the same that describe the response of a fluid to an external perturbation, which is the probe in this case, okay? But it's most important that the external perturbation is weak. Let us suppose you do a light scattering experiment of a fluid at a certain temperature T, and you start heating the fluid. Then forget about the publishing, about equilibrium properties. You are heating the fluid. And then there are other physics, of course. Physics, thermodynamics of non-equilibrium, and the dynamics of non-equilibrium is a whole other field. It's very important to take care of all these things. As far as you are in the linear response theory, we can talk about experiment measuring equilibrium properties. Okay. So, to introduce the correlation function, let us consider a fluid in thermal equilibrium at a certain temperature. Since in the equilibrium, the number density and the temperature averaged do not change with time, and their value are homogeneous in the fluid, so let us suppose that we have a volume V that contains n molecules, each with mass m. And let's suppose also for simplicity that the molecules do not have internals degrees of freedom. Water can have also internal degrees of freedom, but for simplicity now, let's suppose it is not. Of course, if we introduce them, we know how to deal with them, just to keep things simple. So let's suppose that, for example, also two molecules of water interact only through central addictive two-body potential. This is also a huge approximation, the two-body potential approximation. If you are inside the field, you might have heard of three-body potentials, four-body potentials, so to calculate also the terms due to the interaction of three. But of course, these are in any case effective potentials. So you will see in the case of water that they work very well to study certain kind of properties, not all of them. Also, I will tell you again, but we will deal here with the classical molecular dynamics and so classical potential, but, and for all the phenomenology that I will show you, quantum mechanics explicitly taken into account are not so important. But there are several properties of water that you might want to study, for which quantum mechanical effect explicitly taken into account matter. I say explicitly because, of course, our physics is done of quantum mechanics. I mean, a classical approximation are like this because there is quantum mechanics underneath. But if I can approximate a Coulombic with a Coulombic potential plus a Lennard-Jones so that they don't crash, my interaction potential between two atoms, then it means that the quantum mechanics is averaged. I can do that. I can use classics. If I have to calculate the polarizability, for example, of molecule, then I need the quantum mechanics. There are properties in which you need to go quantum, but not for this. So, let's suppose also that the fluid is not close to phase transition, that there are no external fields. So it's invariant for spatial and temporal translation and inversions. Classical, I just said it. The Hamiltonian of the system will be this one. So will be done by a part of the kinetic energy of the entities, which can be molecules or atoms, depending on the liquid, plus the sum of all, so there is a subscript L here, I will correct this error, plus the sum of the pairwise potential central. Okay, so fluids classically treated are governed by the Hamiltonian equation of motion, where R and P are position and momentum, and these are the Hamiltonian equation of motion, which most of you know very well. So molecular dynamics will deal with the Newton or the Hamiltonian equation of motion solved with the finite time. Okay, let's now let us suppose now that we are in the canonical example, which is the MVT, where NV are constant and T is kept on average constant because it's coupled to a thermal bath. So the momentum and position of each particle in time follows a distribution function, which is the canonical distribution function, which is always a probability distribution function, which is this one. And gamma is the 6 n-dimensional phase space, okay? We are in a huge, we have a huge amount of dimension here because each particle can have 3 coordinates and 3 velocities, so 3 momenta. And so we have 6n dimensions, okay? So multi-dimensions. That's why, for example, when you have to do this kind of things, when you have to integrate, it is, in this case, useful to use Monte Carlo integration, for example, if you have singularities, because integration over a lot of dimension can be a royal pain in the neck with normal methods. Okay. What are the observables, like the density? They are microscopic operator. Let's call them generic A of RT, and they evolve in time. These A or B of RT, I want to correlate these. This will be the correlation function. And in particular, as I told you, we are interested in the number density that measure the fluctuation of the local value of the density with respect to the average. Okay, so to this quantity, but the local value of the density is this one, okay? At R and T. This is its local value that fluctuates. So the time dependence the time dependence here from R and T comes from the fact that the single particle is evolving according to Hamilton equation, and of course, it will be, in average, equal to a constant, because the fluid is in equilibrium and it's homogeneous. So we will have also those two relations that are kept valid. It's 12:15. Do you want to make a little break, or do you want to, because we have another 45 minutes. Would you like to make a 10 minutes break? Are you tired? If you're not, we go on. I'm not. It depends on you. Go on with the story? Yeah, especially because we don't break it. You have another point when we can break, but not this one. Okay. So in the canonical example, we arrive to here, which is constant. Okay, the density is constant. Let's see what comes next. When, as I told you, we need to study the local fluctuation with respect to the average value. So we will study this guy here. So rho of RT with respect to the average rho, which was the one that you saw in the picture before. The average of rho RT is equal to the average of R0 because the fluid is homogeneous. There is no privileged origin in space and in time. And so we will focus on the fluctuation. This will tell us the properties about the properties of the liquid. Now, the ensemble average of the generical observable are this. If you want to do an average of the ensemble, you have to calculate the value of this and the weight with the probability, the ensemble distribution probability. So I of RT will be over all the 6n possible coordinates that the system can have. So this is what we call the ensemble or thermal average, okay? Okay, but we need to calculate in the correlation function how these fluctuations are correlated in between them. So finally, let's define this spatiotemporal correlation function of the fluctuation of, for example, two different observables. I told you that we could correlate the same observable or two different observables. We are correlating here two different observables because this is the most general definition. So the correlation function of B and A will be the deviation of A from its average value at point R prime, T prime, and the deviation of B at point RT averaged with the thermal, with the sample average, and then V for normalization. This is it. So since this is homogeneous, the liquid, these quantities depend on R minus R prime and T minus T prime, because there is no privileged origin in time or space. Where the delta, of course, let me remind you, are the deviation of the instantaneous values from its ensemble average. The fluctuation of a dynamical variable with respect to its ensemble average. Okay, so we are getting to the final form of the correlation function, and we are getting to focus on the correlation function we are interested on the most, which are the density-density correlation function. We are getting there. Okay, the density-density correlation function is the correlation function that we will study for water, and it is defined in this way, okay? So it's the correlation of the density with the surface. I start at an arbitrary point, which, for example, I have decided for you today is 0, 0, but remember, there is no privileged origin. It's important that you decide when you start to look in the phenomenon, okay? I always tell to my students, you have to think that you are sitting on a particle and you start a phenomenon. And then you see something happening. At the beginning, I have a ballistic movement, then I see my neighbors and start slowing down, then I go Brownian. But if I sit down on the other particle, that for me at a certain time is already on the Brownian regime, and I start my timer again, she will do the ballistic and then the other, okay? There is no privilege. In the moment in which you sit and you start from that time 0, the evolution of the correlation, and it will be always the same, okay? No matter when you sit. Okay, so in order to make contact with the experiment, neutron scattering in particular, we study, as a matter of fact, not exactly this one, but a related function, which is the Van Hove correlation function, which is defined in a slightly different way. This is the definition. This is just because in the neutron scattering cross-section you have this, okay? So, but the two descriptors, the density-density correlation function and the Van Hove correlation function, are completely equivalent, as you see that the correlation function is equal to rho for the Van Hove multiplied by the Van Hove correlation function minus rho, which you can demonstrate by looking at these two functions. And for a classical system, the Van Hove correlation function, G over T, can be rewritten in this way. So this is the correlation function and its Fourier transform in K, so the F of KT, and then in omega, so the S of K omega, will be the quantities we are interested in the most in this set of lectures. Okay. Now, let's look at the time dependence density correlation function, which is the Van Hove correlation function. Okay, if we are, as we are supposing, to make things simple, because as I told you, we can always complicate them, but we have to start with simple. If we are in an isotropic and homogeneous fluid, then G over T depends only on the modulus of R and of the time. The function G over T can be separated in two parts, the self, I was telling you about the self, and the distinct. So the self is the correlation of the particle with itself, and the distinct is the correlation of one particle with another particle. So do you understand that, of course, the distinct is different from zero only when you have a correlation with other particles. So it will be zero for an ideal gas. The ideal gas, as you might remember when you studied thermodynamics, you know that in the ideal gas, the internal energy, which is the sum of the potential energy plus the kinetic energy, depends only on the temperature. Why? Because the temperature influences only the velocity, but in an ideal gas, there is no potential. So the Hamiltonian of the ideal gas is only the sum of the kinetic energy. Okay, so for the ideal gas, forget about studying coherent phenomena, because I will never correlate with another particle, because I have no relation with that other particle. Zero correlation. Okay. But you will have the self. I will correlate with myself. Very selfish. It's a very, very selfish amount of particle, those of the ideal gas. Okay, so you can have self and distinct. But remember that when we study the self, if we have a collective phenomenon, then I can see some signature of this collective phenomenon in the self part. Okay? Some of you have studied the solid, and also my colleague this morning was talking about those things in solid. You know, the solid have phonons, so vibration then can go. So a phonon is a typical collective phenomenon. No? It's not me that I'm moving myself. I'm moving with. So when the wave goes, we go all together. So typical collective. Though, in spite of that, you will see signature in the self, because of course, if I have a wave that is passing through me, I go up and down, so my correlation with myself will have the signature of that wave. So if we have collective phenomena, there are some cases in which it's more useful to study only the coherent part. When we have but the self part will give you information about the collective phenomena. When we don't have collective phenomena, you only have to study the self part. Well, you have other constraints, as you've heard this morning. For example, when you study neutron scattering, nature can twist your willing as she wants, because as you know, as you have heard, this depends on the scattering length. Some on the B, on that B coefficient. For example, for water, the self scattering function is incoherent, so particle with itself is very important, because when you do measurements of water, hydrogen has a huge incoherent cross-section, huge, while the coherent of oxygen and hydrogen is ridiculous. So you only get the self when you have hydrogen. That's why sometimes you read about isotopic substitution, which is useful to calculate all the G of R, but it's also useful in order to see the coherent part, because when you put hydrogen, it's only incoherent you're going to get with neutron scattering, okay? So, so we have the self and distinct. So the self will be, as you see, the sum only on E, so E at 0 and E at T. And the distinct is the sum of E and and J different from I, of J in 0 and R in T, all averaged, all thermal averaged. In the limit for t equal to 0, the self will be a delta. What is the probability that I am in 0 if I am in 0? 1. This is a density of probability, so if you integrate, it's normalized to 1, and me, normalized to myself, I'm in 0, 1. I'm 1 and I'm in 0. Probability delta is the delta. The integral of delta gives you 1, okay? If you have the distinct, the probability will be the rho times the G of R. You know the G of R because you have seen it already in the past lectures, okay? So the distinct at 0 allows you also to, R and time equal to 0 allows you also to measure the G of R. Or the other way around, if you know the G of R, you can calculate the distinct at time equal to 0. Then we have some, where am I? Then we have some rules, which is that the integral of the self-intermediate scattering function is 1. The self-intermediate scattering function is normalized to 1 because it's a single particle, property, so we normalize it to the single particle. As you have seen in physics, your normalization is arbitrary. I decide what I want to normalize. We normalize the self to the single particle and the distinct to n minus 1 if you have a fluid that is done of n particle. And then we have also the limit for r that goes to infinity. When r goes to infinity, the probability that I am correlated with with the position that I will have in the infinity is 0. Because I will have forgotten by the time I arrive to infinity where I was at t equal to 0. I will forget. There's no correlation that can extend so long. While the distinct goes to the density, because this is the correlation with another particle. So on the average, at infinite, it will be like a uniform distribution of the other particle. I am still in 0, and the other in infinite are uniform, okay? Here they are. After we did talk so much about them, now we see how they behave. So this is the Van Hoove self-correlation function. Now this is important. This function can be plotted in 2 ways, of course. So you can leave r constant and plot it as a function of t, or you can leave t constant and plot it as a function of r. Now concentrate on the meaning. When you leave t, the time constant, which is what I'm showing you now, what you're seeing is the probability, the distribution, this is the self, okay? The distribution of probability that if I was at time 0 in the origin, for example, after, let's say, 0.1 picosecond, I will be in another R. Of course, these are central potential. So I have already, actually, I should have written 4 pi squared G self, because I have already integrated out all the angular part, okay? So it's only R, which is not a vector, because it's a radial potential. Okay, so this is the probability that if I start in 0, I will be around the place where I started after, let's suppose, 0.1 picosecond. That over there, as you see, at the beginning, if tau is very small, I've used here the relaxation time, which I still did not introduce it. I will do it in maybe tomorrow, later on anyway. If t is much smaller than a certain time characteristic of the system, you are very close to the origin. If time increases, you get farther and farther. But in the meantime, the correlation between my position and where I was at time 0, it's louder and louder. You see, if I started here and I am a small time, I will be in the immediate surroundings. But if I wait a long time, I may be everywhere. There is no more peak of probability of certain zones with respect to the others. Okay? Do you understand? So this is the self part, and this is the distinct. The distinct, instead, has a typical behavior of the distinct, which is for t much less than tau, is equivalent to the radial distribution function, the static density correlator that you saw it already this morning. Is equivalent to that because the time is extremely small, so I'm practically measuring exactly where are, like in a snapshot, what you do with the G of R, where are the other particles when I'm sitting here. You do a snapshot. It's like almost like a static, because the time is very small, okay? When you instead increase the time, you see that also in this case, the correlation become weaker and weaker, and eventually they tend to the rho, so to the ideal gas limit. The self part, the short time of the self part here is a Gaussian, and we will show it later or tomorrow. Okay. The relaxation time is of the order to 10 to the 12th second for this system that I'm showing now. Okay, so you saw this correlation function in the direct space, so RT, but instead of showing a multidimensional graph, I repeat you, I'm showing it the curves for a constant t. I integrated all the angular part, so you see only the radial part, because it's a central, we said the potential is central, okay? So the interaction between the atoms of the particle is center of mass, center of mass. Okay. Now, it's useful to study dynamics also looking at the density correlation function in the KT space and K omega space. The first one is called the intermediate scattering function, and as you see, is exactly is exactly like the direct one. So I wrote it here formally as a thermal average between the density, the fluctuation of the density in the KT space, where the fluctuation of the density in the K space is defined like this. And this is exactly, as you might remember, the Fourier transform of the delta function. Okay? Do you remember this mathematical, this you have done in your mathematical course? Fourier transform of the delta function is this one. Okay, so it is related to the Van Hove correlation function in this way, is the Van Hove minus rho, so it's almost is Fourier transform. And in the K omega space, and this is also always to do with the experiments, as I told you. These different definitions are, because so we calculate them in molecular dynamics, we calculate Van Hove correlation function, f of qt, self-intermediate scattering function, dynamic structure function, and we can make contact with the experiments. So we change some normalization, something. But they are basically one, the Fourier transform of the other. So the second is a dynamic structure factor, S of k omega. And as you see, is directly the Fourier transform of the self-intermediate scattering function of this one. Okay, so these are three very important correlation functions for our purpose. So for the study of the glassy dynamics of liquids and water in particular, these correlation functions are very important. I will show you tomorrow, the day after tomorrow, a theory which is called the Mock coupling theory, which work for supercooled liquids is simple and also did work for water, does work for water. And I will make use of these correlators. And so you will see them. You will see how they behave for a glassy liquid. We are now seeing a simple behavior. The one that I showed you before, it was a simple behavior. Now we will see some other simple behavior for this lecture and the beginning of the next. But then we will go to the glassy behavior, and we see how these correlators are modified by the fact that the liquid is becoming glassy. Okay. Very well. Let's again make contact with the experiments, and so I will in particular focus on the incoherent part of the self-intermediate scattering function. This is because, as I told you, can also have signature of collective effect, and we will see one I have to remember to tell you when we arrive. It's called boson peak. We can see the boson peak, which is a collective effect inside the self-intermediate scattering function. I will show you where it is when I will show you the results of my calculation. But I will deal with the self because with neutron scattering they only measure the self, and also because also for the physics, because the behavior of the particle, the self, with the correlation of the particle with their self are very easy to understand when we talk about the glassy dynamic. But the self-intermediate scattering function is related to the neutron scattering cross-section. I don't remember if this morning you were seeing this notation. This is the typical way in which a cross-section are written. This is the solid angle, and this is the infinitesimal solid angle, and this is the infinitesimal frequency. The incoherent is connected with fs of k in this way. This is the usual kinetic factor. This is the length scattering, which you have seen about this morning. And this is the Fourier transform. Hence, this Fourier transform is also connected with the G self and with the self-intermediate scattering function, which is this. So you see that in the incoherent neutron scattering cross-section, you have inside the self-intermediate scattering function. This is very nice about neutrons. A neutron is a technique in which cleaning the data is very difficult because you have a multiple scattering, because you have the cell that you have to take off. It's for experimental, it's a royal pain in the neck. But once you get the clean result, this can be direct, is the density-density correlation function. So you don't need to make another model to understand what else is happening. The cross-section is much more straightforward. It's more difficult technically. You have to clean up a lot. You have multiple scattering. You have to remove so the neutron touches a particle, but then you want only that result. But then it goes and touches another one. So you see the difference in space or momentum that you measure due to two collisions. You don't want that. So you have to get rid also of this multiple scattering, which is another pain in the neck for neutronists. But once you remove all this pain in the neck, you get a prize, which is a very beautiful cross-section, which is directly connected to the physics you're interested about, which is that of the density-density correlation function. Okay, so we will keep this in mind for the next lectures. And so this correlation function that I have defined are applied to the diffusion of the atom in a fluid. In particular, we will consider three regions in the time to come. The short time region will correspond to a situation in which the particles still do not interact. It's called the ballistic regime, and is similar to the limit of the dilute gas. Here, we have only the self-dynamics and no collective phenomena. So you have to think about this. You are let us suppose we're all moving here, okay? And we all feel each other. So I cannot go too close, for example, to you because I feel it, and then we cannot get too close, and then you influence my movement, I influence yours. I start my clock And whenever I start it, there will be a lapse of time in which I don't feel any one of you. I'm alone, I'm ballistic. Then I get too close and I start feeling, and this, depending on what temperature you have, can come in two ways. One is that, especially upon cooling, you start going slower. We all go slower. And if we all go slower, I succeed in having correlation with you in an intermediate time region, okay? Because we go very slow. If we go very fast, no, we pass from ballistic to the long time limit practically immediately. If the liquid starts becoming denser and taking off kinetic energy, lowering temperature, then I can start to have local correlations with you. These local correlations are what we have to introduce them in the equation of motion of liquids, which is the Langevin equation. We can briefly talk about that, with the memory effect. I have to put the memory effect without this. So a retarder nucleus, which allows me to take into account the fact that we are correlating at an intermediate time. In the long time limit, for length scale greater than the mean free path, we are in the hydrodynamic limit, and experimentally it corresponds to phenomena like in the long wavelength with neutron or light scattering, and in the long time limit we have frequent collisions, and we are in what we call the Brownian regime. I will spend some time about the Brownian regime today and maybe also tomorrow, because I want you to see how these correlators are in the Brownian regime. The self-intermediate scattering function, the Van Hoff, and the Van Hoff correlation function, and the dynamic structure factor. In the Brownian regime, the memory effects are negligible. Okay, so we have ballistic, intermediate region with memory effect, and then long time limit in which you have Brownian motion. So it's the random walk of the drunk person, the drunk random walker, famous drunk random walker. Okay, so let me see. Okay, let me say something else about the thermal motion in liquid. At a microscopic level, even if the system is in equilibrium, as you know, the thermal motion induce the particle to move continuously. In the dilute gas, there are very few collisions between the particles, but in dense phases, as it can be a supercooled liquid, the atom can have this memory effect. So we will see that in the case of supercooled liquid, the memory effect will consist in a cage, which is formed by the first neighbors. What happens in this case? I will have time to retell it also with the picture, but let me start telling you, so when you will see it again, you will remember. I'm here at time equal to 0. I start moving and I don't feel you, okay? Then all of a sudden I start feeling the potential of my first neighbors first. But my first neighbors are very slow. They're not moving very much. So they entrap me in their own cage. They form around me a potential cage, and I cannot go out of the cage. So what I do, I rattle in the cage. So I have like a vibration in this cage until you, my first neighbor, are around me and don't let me go, okay? Then, oh sorry, all of a sudden, okay, sorry, it's the jet lag. Then I think it's I arrived yesterday at midnight, now over midnight from Rome. It's only 5 hours, but it's, yeah. Must be the jet lag. Okay, so what I was telling you. Okay, so the first neighbors don't let me go, so I rattle inside the cage, and I go with frequency that are usually 1,000 hertz, with some similarity with vibration in solid. However, my neighbors are not rigid. At a certain point, they start moving. And when they start moving, I'm free to go. When I'm free to go and I diffuse, I go finally to this Brownian regime again. So, short time ballistic, average time rattling in the cage, long time Brownian diffusion. Got it? This is a typical movement of an atom or of a small molecule if it's undergoing a glass transition, if it's supercooled. We will talk about supercooling. Supercooling means cooled below the melting temperature, where the equilibrium state would be a crystal, and instead I force the liquid to be metastable and liquid. We will talk again about that, but you see in this very condensed course, I have to go back and forth in order for you to have the whole picture. Okay. Single particle and collective effect can be distinguished one from each other. For example, the sound velocity, transmission of sound in liquid, the thermal diffusion are usually related to density correlation effect and sound velocity to collective effect. As I told you, this oscillation in the cage have a relation with the oscillation in the single crystal, but you know that in the single crystal, the harmonic approximation works very well, and they are normal modes of vibration having a precise relation between the oscillation frequency and the wave vector, which is called the dispersion relation. Okay. Now, I would like to talk to you about the Brownian regime in order to show you how are these correlators in the Brownian regime. But since it's only 10 minutes left and we didn't do the break, I would stop it for today, because this is a new part. This is a right moment to stop, so that tomorrow you take again you will follow a whole story. We finish a part of a story. We finished a chapter. So tomorrow we can start the new chapter. Before we go, questions? Curiosities? Was it okay? Was it clear for everybody? Also for those who did not have an introduction in statistical mechanics? I saw some you did. Yeah? Yeah, with the correlation function, you can use it to calculate relaxation times, for example, of the system that give you the characterization of the system. You can recover thermodynamics if you go to, for example, Q equal to 0 to limits. You get also for example, you can get isothermal compressibility. You can get some thermodynamic variables, and you will see in the next lecture all the quantities that we can get out of this correlator. Yes. Other questions? Yes. Yes.
When we run the molecular dynamics simulation, in each step, we carry out some error of the positions of the molecules. How it affects the ergodic hypothesis?
Okay. By this. Yeah. Error with the position are not particularly important because molecular dynamics simulation are rather precise. We do some error, but they really are not so important. What is important is the size and the system and the time we run the simulation, especially the size. Size is a very important thing that matters, but not always. And in particular for the ergodic hypothesis. This depends on how long-ranged are the correlation. Because the problem is this, I'm doing simulation in a finite box, okay? So I will put all the statistics and the correlation of that length. Then of course I'm putting periodic boundary condition, but this is only to avoid the border problem. That it will not save me from the physics that I'm cutting away because I have a finite system. These, of course, affect the ergodic hypothesis because there are some configurations that I will never take into account because I did not put a system large enough. Okay. Luckily, for the simulation that I'm going to show you, this thing is not so important. We can still do the average over time. We still get a phenomenology which resembles very much the experiments, so we know that it's okay. But of course, the potential is the potential that we decided. You always have to make contact with the experiment because ergodic hypothesis needs to rely also on a large enough system. Other questions? Yeah. No, but for a particular reason. I have to thank my older colleagues who demonstrated that there is this finite size scaling. It's a very interesting theory which they shown, which is this. You have to do a scaling. So the critical point will show up in a small system in a different location. Okay, different location. And then you do a small system, a larger one, larger, and then you extrapolate at infinite size where precisely is your critical point. Because what happens in that case is this. Critical points happens when the correlation length goes to infinity. But if you have a finite size, the critical point happens when the correlation length arrives at the border of the box, so before. Okay, usually it happens before. But then there is a precise demonstration of how to, and also how to make finite size scaling. I did it in a paper of mine. I can show it to you. But there are also many other papers in which I localized the one critical point for the Agla potential for water, the liquid critical point for Agla potential, and I used the finite size scaling. But finite size scaling is a well-known technique and with a demonstration that has been used for many other critical points to calculate them with simulations. Otherwise, yes. Otherwise, I mean, if you have it, it means that also the infinite system has it. Okay, but you don't locate it exactly unless you do finite size scaling. There is a very big advantage of finite size scaling in case you do it in your life. Let me tell you this very important thing. You can start also with a very small system because the problem of finite size scaling is you have to enlarge and then after 4 steps you don't have computer time maybe. But start with very small. It's okay. I mean, the theory doesn't have any requirement for that. So my advice, if you have to do finite size scaling, start small and then you enlarge according to the rules. Other questions? Okay, so see you later. I will be here and see you also tomorrow for my next lecture. Thank you for listening. It was a pleasure. Thanks.